All right, so today we're switching gears. We're not switching gears on problem. I'm actually going to keep working on the same problem. We're going to switch models. Until now, we've been focusing on sequential computation in a traditional von Neumann machine, one thread of control. Today, we're going to be talking about parallel algorithms. And the reason we'll talk about parallel algorithms in this class is that it lets us show applications of another really cool idea from randomization, which is symmetry breaking. And actually, I can start the story of symmetry breaking with a really famous example that some of you may have seen, which is the Ethernet protocol, which is used to network computers just about everywhere in the world and has lasted for 40 years already, maybe 50, pretty much unchanged. And like all of your local area networks are running Ethernet of one sort or another. The basic problem that Ethernet is solving is that you've got a bunch of computers on a wire. That want to send messages. And any one computer can send a message by putting a signal onto the wire, and all of the other computers receive that signal that's on the wire. The problem is that if there are two senders who both put a signal on the wire, then what you get is gibberish. And nobody can understand anything that anybody said. Okay, so the problem is you've got this single channel that everybody is fighting to access. And the question is, how do you develop an algorithm that will sort of mediate between all of these computers, right? And without knowing ahead of time which of them want to talk, how can you how can you sort of arrange for them to talk one at a time so that everybody's messages get through? And it's not very hard to see that this boils down to figuring out who gets to talk first, right? If you can just figure out a way to let one computer talk, then it reduces the problem by one, and you can reiterate your solution, right? But how do you get that? How do you decide which computer gets to talk? The problem is they can't really negotiate because the only way they can communicate is on the wire, and if they try and talk on the wire, you've got the same problem, right? So they can't really make any plans together at the moment. You can, of course, design an algorithm ahead of time, but now you've got this nasty symmetry problem, right? All these computers, if they wake up today, they're all in identical states, and some of them want to talk, and so if you've developed some algorithm to decide whether to talk or not, right, you may say, well, there might be some other computers that want to talk, so I'll wait a certain amount of time, and I'll see if they talk first, and if they do, then I won't talk. The problem is that if all of the computers are running this algorithm, then when they wake up, they're all going to wait for exactly the same amount of time to see who else wants to talk first, right? So the question is, how can we get out of this symmetry problem? A simpler version of this is when like two people are walking towards each other, and then you do that little dance where you kind of both move right and both move left and both move right and both move left, right? Because you're kind of running the same algorithm in mirror form, and so you never actually get out of contention until you get lucky. So what trick might we introduce in order to break the symmetry of all of these computers using the same resolution process? Yes? Randomness, right? Randomness is a great way to break symmetry without any coordination, right? For example, if you have n computers that want to talk, okay, and we don't know n at the beginning. I'll come back to that later. But imagine that each computer talks with probability p, chosen independently at random. Okay? what are the chances that a message gets through? Probability that we get exactly one talker is what? Yeah?
P times 1 minus P n minus 1 times n.
Exactly. What distribution is this?
Binomial.
This is the binomial distribution, right? We're asking for the odds of exactly one success with success probability P, right? Where success here means a broadcast, right? Great. In particular, if P is equal to, let me say, theta of 1 over n, then this becomes theta of 1 times 1 minus, how do I want to say this? Theta of 1 over n to the n minus 1, right? So here we have 1 minus 1 over n to the n, which is E, right? My favorite approximation. So this is all, sorry, let me write it out more carefully. This is E to the theta of 1. And so all of this is theta of 1. So if you have a transmission probability of about 1 over n, then you have a constant chance of somebody successfully communicating and taking care of one of the messages that needs to be sent. Right? Incredibly simple algorithm. This was sort of one of the core insights that allowed for the development of the Ethernet protocol. Bob Metcalfe invented it while he was at Xerox PARC. He's at MIT now, actually, part of the time, working on entrepreneurship and such. He had a very successful career, and Ethernet was a big part of it. Okay, small problem. Seems that in order to set P, we need to know N. Right? What can we do about that? Yes? Great. So this takes us to this famous idea in networking of exponential backoff. Right? You can try P equal 1. Everybody broadcasts. If you fail, then you can try P equal a half. If you fail again, you can try P equal a quarter. Right? You can just keep on dropping the probability exponentially. And one of these probabilities will be theta of 1 over n. Right? Yes?
So when there's like a gibberish sent out, you like the computer to know that?
Yes. Yes. In fact, in the Ethernet protocol, this is formalized. When a machine detects a collision, it actually sends a jamming signal onto the wire that makes sure that everybody knows that a collision happened. And there are sort of built-in durations in the protocol that say, wait this long to see if there's a jamming signal before you decide to actually pay attention to what's on the wire. Okay? And in practice, it's more sophisticated than this, right? Once a machine is able to broadcast like this, it kind of takes temporary control of the wire, and it gets to broadcast for a while, so that you don't have to spend all of your time on this symmetry breaking. But this is the core idea. Okay? All right, so exponentially decaying probabilities. You reach theta of 1 over n in order log n steps, right? And again, this too can be made more sophisticated, right? You don't sort of restart from p equal 1 all the time. You run this for a while, and you're operating at a certain estimate of n, and what you notice is if there are more collisions, then you decrease the estimate. If there's a gap where nobody transmits, then you increase or sorry, if I said it the wrong way around, but if there's too many collisions, you increase the estimate for n. If there are not enough collisions, if there's too many silent moments, you decrease the estimate for n. But you do it in these sort of powers of 2 so that you rapidly home in on the correct value. And the reason that powers of 2 is good enough, that's why I wrote a theta over here, is that as long as you're within a constant factor, you have a constant chance of success in your broadcast. And again, you can play with what should the exact factor of multiplication and division be. All of this has been optimized for practice. But I think this is a beautiful one-board example of how randomness can be so powerful for breaking symmetry. And you can see this is a parallel problem, right? You've got all of these machines that are trying to operate at the same time, and randomization is fundamental to making that work. So any questions about it? Yes?
So we don't have a not like this succeeds with less than 1 probability. Because like let's say n equals 4, then maybe that equals 1 over 4 succeeds with like 1 over e probability.
Yes.
But all of the other ones succeed with very low probability.
Yes.
So then how do you decide when to stop?
Well, again, if you keep on increasing your estimate for n, eventually you're going to start seeing silence because nobody's going to transmit. And that tells you that you've overshot, so it's time to start decreasing your estimate for n. Right? So basically, a collision means you should increase your estimate. A silence means you should decrease your estimate. And so you get this sort of oscillation around the correct value. Okay. All right, so I was able to tell this all to you pretty informally. If we want to study parallel algorithms in a more formal sense, we need a computational model. And those of you who took advanced algorithms with me last year got a couple of lectures on this, which I'm not going to repeat. I am just going to mention that we are going to use the NC computational model. I should say the PRAM model, which says that we have a let's just say many processors synchronously computing and reading and writing one giant shared RAM. So it's the same as our normal computational model, except there are many processors, and in each time step, each processor can do its own thing. It can do a computational step, it can read a memory location, it can write a memory location. Okay? And this is kind of close to some kinds of practice. Like you can build a parallel shared memory machine. If you have a huge number of processors, it gets complicated and you move to other models, but you can simulate this pretty well on most parallel architectures. And underneath this model, we have a complexity class called NC, which stands for Nick's class. Nick is Nick Pippinger, who is a complexity theorist. He didn't name the class, but his buddy did. And Nick named, his buddy was named Steve, and Nick created Steve's class, which is a different complexity class. So it's always good to have friends. So NC is the set of problems which can be solvable on a PRAM in polylog of n time using poly of n processors. And this turns out to be the sort of right natural equivalent to P for sequential algorithms. It's kind of the best you can hope for, and it is often achievable for many of the algorithmic problems that we care about. Okay? A basic reasoning for this is that you expect to have to do kind of for the kinds of problems we work on, you expect to have to do a polynomial amount of work. And work needs to be divided up among the processors. So you know that either the time or the number of processors is going to have to be polynomial in order to get the work done. right? Why is polylog of n the right thing? Well, basically because of divide and conquer algorithms. These show up everywhere in parallel algorithms. If you think of an algorithm like quicksort, right, sequentially, you say that T of n is equal to 2t of n over 2 plus stuff, right? And this gives you an n log n running time. But when you have a parallel machine, you can run all the subproblems in parallel. You can solve, right? After you pivot, you can sort both halves at the same time. So in parallel, you end up with runtimes like T of n equals T of n over 2 plus stuff. So this works out to n log n and so forth, but this works out to log n. So you can often achieve logarithmic runtimes. Once you've got a library of these logarithmic runtimes, you might want to invoke them as subroutines in your algorithm. And so if you have an algorithm that runs in log n time and your algorithm invokes it log n times because it's a divide and conquer algorithm, all of a sudden you're a log squared n time algorithm. So this is why we tend to get polynomials in log n, okay? It's because of the way we compose algorithms. We put a limitation of polynomially n processors because basically if you have infinitely many processors, they can try all the solutions at the same time and sort of solve the problem trivially. So with a huge number of processors, you can basically do anything, and it's not interesting anymore. Yeah, question?
So for an infinite amount of like processors, is there still like communication overhead?
Not in a shared memory. Well, it depends on your definition of they can all. This is why it's not entirely practical, right? You can't actually build a machine where every processor can write to the shared memory in the same cycle, right? There may be issues with getting information into the processors, and so yes, you can put communication bounds, but some problems just become trivial when you use an exponential number of processors, say, in uninteresting ways. So this is really all I want to say about why we're using this complexity class. Have I made a reasonably convincing argument for it? Yes?
My other question is, why are we not using a fixed number of processors?
Well, if you fix the number of processors, but you allow the size of the problem to grow, right? A fixed number of processors can only give you a fixed amount of speed up over a sequential algorithm, right? If you have 10 processors, you can only run 10 times as fast as a sequential algorithm because you can always simulate those processors on a single processor, right? So if the number of processors does not grow with the size of the problem, you're basically going to see the same runtimes as the sequential case. Other questions? Okay, so as I said, lots and lots of problems have NC algorithms. Things like the basic arithmetic operations, plus, minus, times, division, right? And they have these algorithms in a strong sense. You can add or multiply n-bit numbers in log n time, right? Which is actually kind of cool. It means that like no one coming to the communication complexity issue, no one processor is ever going to see the whole number, right? There isn't time for it to look, but we can nevertheless achieve really fast operations, right? If you think about addition, this is somewhat surprising, and one of the things I teach in the advanced algorithms class, right? How do you do addition without all the carries happening? Well, it turns out you actually can divide and conquer the movement of the carries so that no processor needs to see a lot of it. Okay. We can also do things moving up a step like matrix products. Right? A matrix product is a bunch of vector products, right? So, and how do you do a parallel dot product? Well, you need to multiply corresponding pairs of numbers, but that can all be done in parallel. And then you need to sum n numbers, so I guess I should add that to the list as well. So summing or multiplying n numbers is also something that you can do in NC. And if you think about it, divide and conquer is the answer, right? You add the first half of the numbers and the second half of the numbers in parallel, and then you just add the two results. And this gives you a log n time algorithm for adding n different numbers, right? Yeah, so NC is next. Oh, I should also add, because we're going to use it, determinant can also be solved in NC. I'm not going to tell you how to do any of these because they're all deterministic and thus boring. But you can do all of them, right? Determinant is not trivial. It actually turns out that the way you compute the determinant is by computing the characteristic polynomial, which is much more complicated, but there doesn't seem to be any way to compute the determinant directly. But there are these weird identities that let you compute the characteristic polynomial by doing lots of matrix products. And matrix products can be done in parallel. We will be talking about RNC, which is randomized NC and is the analog of RP. So this is the Monte Carlo randomized parallel algorithms, and also ZNC, right, which is the Las Vegas ones. And we have all of our standard techniques for transforming Monte Carlo algorithms into Las Vegas algorithms and so forth. I will also say that, as with polynomial time algorithms, the first question you always ask is whether something is in NC, right? Whether it can be solved, just like you ask whether something is polynomial time solvable. Once you know that it is, then you can spend years trying to figure out exactly how efficient you can make it. How close, right? How close to constant time can you make your parallel algorithm? How few processors can you get away with using? But the first question is just, is it in NC at all? Okay. And I'm actually going to focus on that. I'm not going to really work at optimizing away the exact polylogarithmic bound or the exact number of processors. Okay. All right, so as I said, we're going to change models, but we're not going to change the problem. We're going to keep talking about matching, bipartite matching. Okay. And last time I showed you that there's this really bizarre connection that you can solve, you can determine existence of a bipartite matching by taking the determinant of, and I actually misspoke, I called it the Edmonds matrix, but when it's a bipartite graph, it's called the Tut matrix. Okay, so the Edmonds matrix is for a general graph, it's the adjacency matrix, but with these indeterminate variables filled in, right? The Tut matrix is specifically for a bipartite graph where the rows are one side of the graph and the columns are the other side of the graph. So it's a special case for the bipartite graphs. Is a non-zero polynomial. And from that, we concluded that if that's true, then with high probability, a random assignment of values to the indeterminates will let you compute the determinant and see it's non-zero. Yes, this is what we spent last time on. And I just told you that we can compute the determinant in parallel. So that immediately tells us that existence of a perfect matching is in NC. Right? Because obviously you can parallelize the generation of random values in the Tut matrix, and then you can compute the determinant using the boring deterministic algorithm that I haven't bothered to tell you about. Yes? Okay, what was the next step that we took? Yes? Absolutely. This is a Monte Carlo algorithm. Yes?
The next thing you did was like you moved the edge.
Yes, and why did we do that? What were we trying to do?
We're trying to generate.
Right. So to generate a perfect matching, right? We used this self-reducibility idea. Right? We take away an edge. We have our perfect matching tester, right? Which only returns a non-zero if there is a perfect matching. Right? So we take away an edge, we run the tester again. If the perfect matching has vanished, it tells us that we needed that edge, and so we'll put it into the perfect matching. If the perfect matching has not vanished, it tells us we didn't need that edge, and so we will proceed. And so we go through one edge at a time, checking which edge belongs in the perfect matching and which doesn't. And at the end of all that, we have our perfect matching. Yes? Okay. Why is that a problem today? Yes?
If we do it just really good last time, you just do it at a time, and then now outside the point launch now.
Exactly. One at a time is never how you want to do things in parallel, right? If we're checking one edge at a time, it's going to take us m sequential determinant steps to decide what is the perfect matching. Right? That's no good. Okay. Can we maybe do the obvious thing? What if we just tried in parallel removing each edge and seeing if it turned out to be necessary for the perfect matching? All right. So we do it one at a time. It's too sequential. So if we try all at once, yeah. Exactly. If there are multiple perfect matchings, you might not need none of the edges might be necessary, right? In particular, if you have a complete bipartite graph, right, then no edge is necessary for a perfect matching, right? So this fails. But you actually mentioned an important reason that it fails, right? Which is that if you have multiple bipartite matchings, then they kind of make each other unnecessary. Right? So if you think about it, this is kind of a symmetry problem, right? If the perfect matching is unique, we can use self-reducibility, right? If the perfect matching is unique, we can, in parallel, right, use a different set of processors to try removing each edge and computing the resulting determinant. This is incredibly wasteful, right? But it only multiplies the number of processors you need by a polynomial factor. So it's still in NC. Okay, this is the equivalent to just being sloppy about your polynomial in a sequential algorithm. So we're going to use a huge number of processors, but still polynomial. Try every edge, remove it. If it turns out that it's necessary, it's in the perfect matching. If removing it did not destroy the perfect matching, then it's not necessary. We test each edge at the same time, and boom, then this works. Right? So the problem is that you have multiple solutions to the problem, and each of them is interfering with the others being discovered, kind of like the Ethernet problem. Yes? So, how can we break symmetry? Yeah?
You do like an nearest shiny graph, you take a subset of the edge.
Yeah, I was actually trying to think through that this morning, whether it would work, right? You could imagine that you set some threshold probability p, and take edges, keep edges with probability p, and discard them with probability 1 minus p, and hope that you get lucky and end up with exactly one matching. And, continuity suggests that there must be some value of p where that has some chance of happening, right? But I'm not sure whether that chance is large enough or whether it kind of is flat very quickly. I'm also not sure how close you have to get to exactly that value of p, right? So I'm going to show you a different trick that was developed by, well, anyway, I'll get there, but you have a question? Oh, you have an answer. Okay. Good. So that is the technique that we're going to use. All right. Which problem did I do that on? Oh, yes. Okay, that was a much more basic assignment. That was basically assigning a random ordering. The weights were just a way to achieve the ordering, right? But yes, so I'm going to show you this idea of Momole-Vazirani-Vazirani. These are a pair of brothers, both very important theoretical computer scientists, Berkeley and Georgia Tech, I think. And actually, Vazirani was the one who introduced me to algorithms and got me really excited about algorithms and sort of determined my career when I was an undergraduate. So they actually do exactly what you said. They introduce edge weights. They showed that in order to find a perfect matching, what they do is they solve the minimum weight perfect matching problem. Which is counterintuitive, but happens more often than you would expect, that solving a harder problem is easier, right? So we set out to just find a perfect matching. We are going to do so by finding a minimum weight perfect matching. Okay. And the first thing that they showed is that this is easy if that minimum weight perfect matching is unique. Okay, we're going to have the same symmetry interference problem with minimum weight perfect matching, but if there is a unique minimum weight matching, we can find it. Where did I put the algorithm for that? Yes. So here's the algorithm. We are going to assign, so we're going to start with our top matrix. Right? We know that the determinant is a non-zero polynomial. And in fact, we know the form of the determinant, right? It's a sum over perfect matchings of a product of the edge weights in the perfect matching, right? That's the Cauchy something form of the determinant, right? So what did they say we should do? Choose random wi's. These are integers. And assign, or call them we's, and assign weight 2 to the we to edge e. Yes?
Oh, yeah. WE.
No. Sorry. So I'm actually right now giving you a deterministic algorithm for the minimum weight perfect matching, right? If the weights make it unique. But the weights themselves do not have to be distinct. It's just that the weight of the minimum weight perfect matching has to be unique. Okay? So if we have sorry, I shouldn't have said random, because we're still working given the weights WE, I am going to assign, sorry for the confusion, value 2 to the WE to the variable x sub e in the top matrix. There we go. So if these are why did we assign these values? Well, if the value assigned to edge E is 2 to the WE, what is the form of the determinant? Yeah? Exactly, right? We have one term in here for each matching. We're multiplying all of the, sorry, I shouldn't call these weights because it's confusing. Let's call these values, right? So we're multiplying all the edge values, but the edge values are exponentiated weights. So we're going to end up just summing the weights, right? The determinant is equal to now the sum over perfect matchings of plus or minus 2 to the power of the matching weight, right? So, if the minimum weight matching is unique, how can we discover it by looking at the value of the determinant? Right? We're adding up all of these powers of 2. Right? Yes? Exactly, right? Every bigger matching is also a multiple of the smallest matching. So the min weight matching is the minimum power of 2 that divides this determinant. Okay? So we have a more powerful result here, right? I first showed you that if the matching is unique, we can find it. Here I'm showing you that if the weight of the matching is unique, the minimum weight of a matching is unique, we can find that. Yes? Correct. We found the weight, but not the matching. But what do we do about that? Now that I have an algorithm that tells me the weight of the minimum weight perfect matching, how can I find that minimum weight perfect matching? Any new hands, maybe? Yes? Exactly. If we remove an edge and the weight of the minimum weight matching changes, we know that edge was part of the original minimum weight matching. If it doesn't change, then we know that the edge was not. And again, since this is a unique minimum weight matching, we're not going to get interference between different matchings. Only the actual minimum weight matching edges will cause a change, and the others will not. Yes?
What if the minimum weight and the non-minimum weight have a common factor?
Well, remember, because we've chosen these powers of 2, right? The common factors is just that the minimum weight perfect matching, the 2 to the power of the minimum weight divides every matching, because all the matchings are just powers of 2 in the determinant. So there are no other factors.
But what if one is
Well, that's fine, because that means that 2 to the 2n is going to divide 2 to the 4n, right? And so when we look for the smallest power of 2, that's going to be the one. Yes? Good question. I was hoping somebody would worry about this, right? So, wait a minute. Right? I said exponentiate all the weights, but that means that if you have a weight of value n, your number is going to be 2 to the n, right? Oh, so actually, just so I don't forget, I'll mention here we can find the matching with the same self-reducibility trick. Right? And in parallel, right? We try all of the edges in parallel. We don't have to do one at a time. So, worry, big numbers. Right? If we have, if the weights are some polynomial values, that means that 2 to the WE has poly of n bits. So when we're trying to compute our determinant, we're going to have to be adding n-bit numbers, multiplying n-bit numbers, subtracting n-bit numbers. Is that a problem? Yeah?
I had a question actually. Just to clarify, should it be biggest power of 2 and not minimum? I think that was my confusion.
I think it's smallest, right?
Wouldn't that always be 2?
Not necessarily, right? Because right, you're summing these different matchings. Many of them are very large powers of 2, right? And then you're going to have this one small power of 2. That's going to be the
Isn't it large? Like 2 will always divide it because they're all 2 by 2.
Oh, I'm sorry. This min. Yes, sorry, you're right. This is a max. You're looking for the smallest power of 2, but you find it by looking for the biggest power of 2 that divides the number. Thank you. Okay, back to my worry. It looks like in order to do this, we're going to have to multiply and subtract and add n-bit or polynomially number of bits numbers. Is that something to worry about? Yeah? Exactly. We can do this in NC, right? As I sort of sketched out. So this is not something that we do in the normal course of events, right? We generally like our numbers to fit in a machine word, so we can use the hardware in order to do constant time addition and subtraction and so forth. But technically, you can do big number addition, multiplication, and subtraction in NC, right? And again, thinking about how you design parallel algorithms, right? There is a parallel algorithm for computing the determinant, right? Which involves it involves a polylogarithmic number of steps. In each step, you're going to be doing some additions or some subtractions. And so each step is going to require invoking these subroutines for addition and subtraction. So the addition and subtraction subroutine will take log n time or polylog of n time, right? And that means that will compose as another polylogarithmic factor on the runtime of the overall determinant algorithm. But the overall algorithm is still going to be polylogarithmic. Make sense? Yeah? Okay, great. So this all works great if the weight of the minimum weight perfect matching is unique, right? How do we make that happen, right? We start, like, we're trying to solve a basic perfect matching problem. There aren't even any weights, right? So how do we pull weights out of a hat so that the weight of the perfect matching is unique? Any ideas for generating some weights that make a, yeah? Ah, good. That actually does work, right? You could make the weights so different that two different perfect matchings cannot have the same weight. So one way to do that is to make the weights of different edges be 1, 2, 4, 8, 6, right? Make the edge weights be powers of 2, right? Because now if you sum two different sets of edges, you're summing two different sets of powers of 2, and you end up with two different numbers. What's the problem with that approach? Yes? Exactly. So if you use really huge numbers to make different weights, which is useful in certain settings, you end up with values that are exponential, which means that after exponentiation, you've got an exponential number of bits to add or subtract, and that you can't do with a polynomial number of processors. Okay, so we need to somehow achieve a minimum weight perfect matching with small weights. Yeah? Oh yeah, maybe we should just try random weights. So this was the main technical contribution of MVV, something called the isolating lemma. It says that if you have any family of distinct subsets over variables x1 through xm. Okay, so you just have m different variables, and you have different subsets of those variables. Okay. In our application, of course, the reason I said m is that we have one variable per edge. Right? Imagine that you assign random weights from the range 1 through 2m to every variable. And when I say random like this, you should always assume I'm talking about independent and uniform. Right? Then the probability that you have a unique min-weight set is at least a half. Okay. So again, I think this is quite shocking at first glance, right? We could have as many as 2 to the m different sets, right? You can even have like 2 to the m over 2 sets that are not, where there's no containment relation, right? Where every pair of sets differs on some of its contents, right? No set contains another. You assign weights from really a quite small range, right? This is fine for our purposes, right? You end up with a likely unique set. Yes? So this is what's interesting. This is a completely general statement that has no dependence on our being a matching problem, right? This says you have a set of variables, doesn't matter where they came from, just m variables. You want to know about the minimum weight set, right? And notice that you're allowed to specify the subsets. This is not only if you look at all 2 to the m subsets, right? Any family of subsets. So in particular, we can take the subsets that correspond to perfect matching, right? But we don't have to. Any collection of subsets is covered by this lemma. Okay. All right. So if this is true, then we're home free, right? We assign random values. We have a 50-50 chance of making the minimum weight matching unique, at which point this simple determinant calculation will tell us the value of that minimum weight perfect matching, and self-reducibility will allow us to find that perfect matching. Okay. So all I have to do is prove this lemma to you. Okay. But let's take a break first and recharge our batteries, and then we will look at the proof. Oh, so since you're sitting down anyway, I put out a message on Piazza that I have to take off for Wednesday for a Jewish holiday, and I could just put up a recorded lecture. But if people want a live one, I may be able to find time to give it on Thursday or Friday, or as a doubleheader on Friday with the regular class. I put up a when to meet to ask you for your availability of times if you're interested. So please fill that out. I'll need to decide within the next couple of hours after class. So I'll take a look at what's there, and if it looks like there's a critical mass for a time that I can do, then I'll see if I can make that work. The piece that will be released on Wednesday night, yes. Yes.
Is that referring to like the distributed caching system where you have like a tree structure?
I think for the
or
problem,
is it just consistent?
problem one is where is the one that I pulled in from the previous week, right? That it's not actually asking you to implement the tree structure or something. It's just asking about which caches are actually going to be contacted by somebody asking for, like, right? Each machine uses its distributed hash function to figure out which cache to ask for the content. And I'm just asking you to prove how many different caches are going to be asked for the content. And that doesn't depend on how you implement the lookup. It just depends on the definition of the consistent hashing function.
I see. Wait, I'm just like very confused about what that problem is asking about. Okay, so it uses like the tree structure.
No, again, the tree is an implementation. The definition of the consistent hashing function is you hash your machines to a ring, you hash your pages to a ring, and the machine that you contact is the one that immediately follows the page.
Okay, and then like...
How you implement that is not important.
Okay, sure.
So now the assumption is that each client only is aware of half the machines. And so those are the machines that it is hashing to the ring, and those are the machines that it is contacting.
So then like the client hashes its web page to a certain position on the ring.
Yes.
And it finds the next machine on the ring that's within its set of known.
Exactly.
Okay. So, but then it has nothing to do with like the structure you described, where like each machine is a node, and like the nodes get the data from their parent.
No, that's the tree. That tree caching technique is for dealing with a single popular page, and that's not what I'm asking about. I'm asking about the original distributed consistent hashing scheme that I defined in lecture for just associating a page with a single machine.
Okay.
Right. With the tree, you end up spreading a page over many machines, but that's not what we're asking about here.
I see.
All right. Let's look at the proof of the isolating lemma. And again, I think that the major insight here was to imagine that this could even be true, because it really doesn't seem like it could possibly be true, right? But it is. And the proof is pretty straightforward once you come up with it, although, again, I think it's quite a clever proof. So what's the proof? Let's focus on one variable x sub I. Okay. So from the perspective of variable x sub I, I'm going to let y be the collection of. This is assuming I've assigned some values, right? So this is all based on the values that I've assigned. So y is min value sets containing xi, and n is n is min value sets not containing xi. So this is just a partition of the min value sets. Okay. Now notice that the true, sorry, I did not say that correctly. This is, let me see how I can make this clearer. Let's put it this way. Min value sets among all sets containing xi. And this is min value sets among all sets not containing xi. So these may be two different values, right? It may be that xi is a huge number, and so the min value sets containing xi I'll have large weight, and the actual min value sets do not contain xi. Okay? And indeed, the true min sets are in Y or N, or possibly both. Right? It could be a tie. Okay. Which is determined by xi. Right? If xi is minus infinity, then the actual min sets are y. If xi is plus infinity, then the actual min sets are n. Right? As you increase from minus infinity to plus infinity, there is a single value for xi where it's both y and n, right? Just a transition point. Now notice that if only y is the true min weight sets, then xi is in every min weight set. Right? On the other hand, if only x is the true min weight sets, then xi is in no min weight set. Sorry, n, yes. Yeah, mathematicians, you understand why I keep saying y and x instead of saying y and n, but normal people would just say y and n all the time. So you've got these two cases where xi is in every min weight set or no min weight set. If both, right, then it's kind of, we'll say xi is ambiguous. Okay. Now my claim is, if no xi is ambiguous, then the min weight set is unique. Would anybody like to justify that claim? Yes. Yes. Exactly. Right? We look at each xi, and if it's in every min weight set, then, well, we take it. If it's in no min weight set, then we discard it. Right? And when we're finished, we'll have discovered all of the x's that we took are in every min-weight set, which also happens to mean that that set of x's is the only min-weight set. Yes? Great. Now we're almost home free, right? Because now we can use the principle of deferred decisions. Okay. So what is the probability that xi is ambiguous? Remember, I'm assigning random values in the range 1 to 2m to each xi. Yeah? 0. Is it impossible for xi to be ambiguous? There's only one value that can be ambiguous. Exactly, right? We're going to use deferred decisions. Right? We'll reveal all the other xi values. Right? We're picking them all at random at the same time, but we're going to look at the other ones. Right? From this, there is a unique value that makes xi ambiguous in this context. Now, that unique value might not be in the range 1 to 2m at all, right? But it is unique. So in the worst case, it is one of the values in the range from 1 to 2m. I love seeing all these nodding heads. This is how I like lecture to go. So at most, one value in 1 to 2m makes xi ambiguous. So the probability that xi is ambiguous is at most 1 over 2m. And therefore, the probability that any xi is ambiguous is at most what? Right? We don't know a lot about this distribution. We can't use Chernoff bounds or Chebyshev bounds or anything like that, right? But what can we use? Yeah? Sorry, what was that? Union bound, right? We just have m different events with probability 1 over 2m. So the union bound bounds the probability by half. Done. So we've now shown that this simple technique generates a unique minimum weight matching, right? Which we can detect using our exponentiated determinant calculation. Okay. So I will emphasize this is an RNC algorithm. It's Monte Carlo because we don't have a certificate, right? I mean, the matching does provide a certificate, but there's a chance that our randomization experiments will tell us that there isn't a perfect matching, even though there is one, right? If we just have bad luck. And we have no way to certify that there is no perfect matching. Okay. So we can't guarantee correctness. We can just make ourselves correct with high probability. Right? This gives us a 50-50 chance of correctness, but if we want more, we amplify it the usual way, or else we choose a larger range. We choose numbers from a larger range, although that will make our numbers bigger. So it might not be worth it. All right? Interesting fact, it is not known whether this problem is in NC. At least last I checked. no one has come up with a deterministic algorithm for finding a perfect matching in the general case, in parallel. Even weirder, there's a generalization of the perfect matching problem called exact matching, which is asking for a matching. The edges are colored red and blue, and you want a matching with a certain number of red edges. Okay? And the exact matching problem is not known to be in P, but we can solve it in RNC. Okay? So in general, right, anything that you can do in NC, you can do in P by simulating all of the processors. So here we have a not completely pathological problem, which we can easily, quote, easily solve with randomization in parallel. But without randomization, we're not even sure if we can solve it sequentially. All right. Any questions about that? Yes? Yes, because anytime you have a parallel algorithm, you can simulate it in sequence with the sequential processor, right? You just have your one processor simulate all of your parallel processors. Yes?
It's open whether P equals NC.
It is open whether RNC is contained in P. Right? It is also open whether P is equal to NC. So like all the things that you've seen in complexity theory carry over here as well. So you're all familiar with NP completeness. We've got this class NP, which is known to contain P, but there are problems that we're not sure whether they're in P or not, so we're not sure whether P equals NP. And they've defined these NP complete problems, which are like the hardest problems in NP. Everything else reduces to them. So if you can show even one of those NP complete problems, if you can give a polynomial time algorithm for it, then the whole hierarchy collapses, and you've shown that P is equal to NP just by giving an algorithm for one problem. There are similar open questions around P and NC, but they're not in this direction, right? The big open question is P equal to NC? In other words, if you can solve something in polynomial time, can you solve it quickly in parallel, right? So NC is a weaker complexity class than P. We know that NC is contained in P because of this straightforward simulation argument. But we don't know if you can take any problem in P and solve it in NC. And actually, you don't have to look very hard for the P-complete problems, right? So P-complete problems are the analog of NP-complete problems. If you can solve one of them in NC, you've solved all of P, right? And one of the P-complete problems is max flow. Okay, so you don't need a weird esoteric problem, but if you can just do max flow, max flow with edge weights, then you've shown that P is equal to NC. But here we have an even weirder question or relationship around RNC because we don't know the containment in either direction. Okay, of course, RNC is inside of RP because you can use your randomness in the simulation. But we don't know about the relationship between P and RNC. Okay. Any other questions? Okay. Let me just give you a little preview of the next question that we're going to be looking at, because it's a nice generalization of the Ethernet problem that we already discussed. And it will give you some fun things to think about until the next lecture. And this is a problem called maximal independence set. And in maximal independence set, you're given a graph G. An independent set is a set of vertices with no two connected by an edge. So it's the complement of a clique, if you're familiar with the clique, with what a clique is. Where a clique is where all pairs are connected by an edge. An independent set is where no pairs are connected by an edge. Okay? Some independent sets are trivial. A single vertex is an independent set. Right? What we're interested in here is a maximal independent set, which means that you cannot add any vertex to the set and stay independent. Okay. In the optimization literature, this is sometimes called a stable set as opposed to an independent set. Okay. Now, the maximum independent set is the one with the most vertices, and maximum independent set is NP-complete. In fact, it's been studied intensively. It's one of the most interesting NP-complete problems. The past decade of research in complexity theory has shown that not only is it NP-complete to find a maximum independent set, it's even NP-complete to find a slightly large independent set. Right? Like the approximation ratios are terrible. Okay? Even if there's an independent set of size n over 20 or something, you won't be able to find one bigger than like n to the epsilon. So this problem is not tractable. Or we certainly don't think it is. The maximal independent set problem is quite tractable. Can somebody suggest a simple algorithm for finding a maximal independent set? Yes? Yeah, greedy, right? Greedy works. Right? Add one vertex, throw away its neighbors. If there are any vertices left, add one, throw away their neighbors. Just keep doing this until you've added all the vertices you can and thrown away all the other neighbors. Right? Each neighbor got thrown away because of some vertex that was added to the set. Therefore, the set is maximal. You can't add anything to it. Okay? Great. We have an algorithm. What's the problem with this algorithm? What's the problem with this algorithm today, given what we're studying? Yes? Sequential, right? You add vertices one at a time. This is going to take you n time, no matter how many processes you have. You can use lots of processors to delete the neighbors quickly, but in the worst case, if, for example, your graph is a line, you're going to take a polynomial number. You're going to take n over 2 steps to build the independent set. So that's bad. So the question is, can you solve the maximal independent set problem in parallel? And we've already started to work at this, because if you think about it, our Ethernet problem was a kind of maximal independent set problem. It was just on the complete graph, right? An independent set on the complete graph is just one vertex, right? And what did we do? We sort of, we let each vertex flip a coin to decide whether it wanted to join the independent set. Right? So with that idea as a starting point, what might be an approach to building a maximal independent set in a general graph, right, where you don't have connections between every pair? Certain pairs are allowed now to both talk. And actually, one application of maximal independent set is in wireless networking, right? If you have wireless nodes, some of them don't interfere with each other, and so they can broadcast at the same time. And so you may want to find a set of more than one of them that all talk at the same time. Okay? So what might be a generalization of the Ethernet strategy that makes things happen well in a general graph? Any thoughts? Yes? Yeah, right? Certainly, if you imagine a regular graph where all the degrees are the same, right, then if we use the same Ethernet coin flipping trick, right, we can say that with constant probability, if I use 1 over my degree as the probability, and my neighbors do as well, right, with constant probability, I will join the set, and none of my neighbors will. Right? Which means that the collection of nodes that decide to join or decide to talk is independent, and you can add them all at once. And when you add them, it will kill all of their neighbors. So you'll make a lot of progress. Okay. Now, if you have varying degrees, it gets murkier, right? If all the degrees are different, maybe I'm talking probability 1 over my degree, but my neighbors might have different degrees. And so their coin flips might not be the ones that I expect, and so that np times 1 minus p to the n, that may not be the probability that things work out. Okay? So it's not clear how to do this, but it turns out that it actually works. If you use 1 over, I think, 3 times the degree, it gives you the starting point for a maximal independent set algorithm, and we will analyze and prove that next time. Okay, check your the Piazza announcements. As I said, I'll look at the schedule and see if there's a time to whether we can present this in person or whether you'll need to see it by recording. And remember, Country Line Dancing Sunday.